All right, so we're going to look at type 1 and type 2 errors in null hypothesis significance testing. So the ways that it can go wrong. You might be familiar with the boy who cried wolf. Essentially, there's two errors we can make in null hypothesis significance testing for the mean: crying wolf when there is no wolf there, or not crying wolf when there is a wolf there. And so today we look into that in a bit more detail. And we're going to use an example. So the brain training scandal. In the 2000s, companies were claiming that their games made you smarter, backed by studies with p-values less than 0.05. In 2016, one of the companies, Lumosity, got fined for deceptive claims. And so we're going to ask ourselves the questions: how did these significance science claims turn out to be wrong? And the answer to that is type 1 errors, as we will come to find out. So also, would you believe this is the very last video on specialist maths? I've done the whole course now online for units 3 and 4. So if you find these interesting, give us a thumbs up, reach out, all of that fun stuff. The courtroom. So a trial is a hypothesis test. In a courtroom, there's essentially 4 verdicts, as we can see in the table here. You convict an innocent person. So you get a guilty verdict for someone that's innocent, a not guilty verdict for someone that's innocent, so that would be correct. A guilty verdict for someone that is guilty, so that would be a correct decision, and a not guilty verdict for someone that is guilty. The first error of convicting or finding someone guilty that is actually innocent is called a type 1 error, and finding someone not guilty that is actually guilty is called a type 2 error. And the legal system is deliberately conservative. It treats convicting the innocent, a type 1 error, as a worse error. And so that's what we're going to look at today in terms of hypothesis tests as well, because that's something that we can set in a courtroom. The evidence must be beyond a reasonable doubt before the jury rejects the null hypothesis. The null hypothesis being that the person is not guilty. The alternative hypothesis is that the person is guilty. So these are the actual strict formal definitions. Type 1 error is a false positive, so you're rejecting the null hypothesis when it's actually true, and a type 2 error is a false negative, so failing to reject the null hypothesis when it's actually false. Here is the table for that information. The probability of a type 1 error is called alpha, and we set that when we're doing our statistical tests, and a type 2 error has a probability of beta, which we'll look at in a bit more detail in a moment. So the claim from these brain training companies was that the apps that they were developing increased people's IQ. But we know if we set a probability of alpha being 0.05, so 1 in 20 tests of a useless program will reject the null hypothesis purely by chance. If you run enough of those small studies and publish only the wins, type 1 errors look like a discovery, and that's basically what happened with Lumosity. The way to get around this was in 2010 when Owen and his colleagues in Nature tested 11,430 people over 6 weeks, and they got better at the train games, but no transfer to general cognitive ability. So people got better at the apps themselves, but they didn't actually get better general cognitive ability. The IQ didn't increase significantly, statistically significantly. And so, the US regulatory body fined Lumosity $2 million for deceptive advertising because they were claiming that these apps were making you smarter. And so what we're going to do is we're just going to make up some numbers to illustrate the point so that we can do a bit of maths with those numbers. So let's pretend that we're a psychologist running a brain training app with n equals 25 people, measuring their IQ on the standardized scale. So the null hypothesis scale being a mean of 100 and a standard deviation of 15. The null hypothesis is that the mean is 100. The alternative hypothesis is that the mean is greater than 100. So that the training works. And the reason we're not saying less than 100 is because we're only interested in a one-tailed test here. We're only interested in the app raising scores, not lowering scores. So we're going to pick our alpha, our criterion, our beyond a reasonable doubt in the courtroom land of alpha being 0.05. That's our risk of a type 1 error. So, as I just mentioned, the probability of a type 1 error is alpha. And strictly speaking, in this language here, language of probability, the probability that our distribution takes on a value greater than or equal to C, given that the null hypothesis is true, aka that the mean is 100, we need that to equal 0.05. And so our question is, what is that value of C? And basically, when we take our 25 people sample, if that value, it turns out to be larger than whatever this C value is, we're going to reject the null hypothesis. If it's less than that, we're not going to reject the null hypothesis. So as it says down here, if the training is useless, this red tail is the chance our sample still lands in the rejection region. We choose alpha, so we choose the risk of making a type 1 error. Again, with our courtroom analogy, we choose the risk of convicting innocent people. So what we need to do now is we need to calculate that C value. So the question is, how big is that C value? What does the sample mean need to be before we reject the null hypothesis at the 5% level? We want C such that the distribution taking on a value greater than or equal to C, given that the mean is 100, is 0.05. The standard deviation is 3. A normal distribution, a standard normal distribution with 5% in the upper tail gives you a z-score of 1.6449. So basically, if you're 1.6449 standard deviations above the mean, there's only 5% of the data in that tail, in that upper tail. And then basically we need to unstandardize. So our C value is going to be equal to our null hypothesis mean, which is 100 plus 1.6449 times the standard deviation. And that gives us 104.93. And so then this is this critical C value that we can then make a decision based on. So if we get a sample mean greater than or equal to 104.93, we reject the null hypothesis and conclude that the training raises IQ. But if it's less than that, we don't reject the null hypothesis. Okay, so this rule is fixed before the data are collected and both errors and both error probabilities flow from it. Okay, we'll look at that now because I think this next diagram will be really helpful. So we've spoken about type 1 error. Let's presume for a second that the training works. There's a big assumption here, but we're going to say let's presume that it works and that the mean, if the training works, is 106. So we can see that in blue we've got our normal distribution with a mean of 100, and then we can see in pink we've got it's now been moved up to 106. And so our critical value, which we just calculated before, was 104.93. Remember, beta is this idea that the training works, but we get a value less than C for our sample mean. We fail to reject the null hypothesis. Now I want to state this clearly. So imagine you had a score of 103 for your sample mean. You've got your 25 people, they'd use the app. You take an average of their scores, they get 103. So they get that score of 103, but we fail to reject the null hypothesis. We've made a type 2 error. So this yellow region represents the area where we've made a type 2 error, the probability that we make a type 2 error. And strictly speaking, mathematically, here is the area calculated. So the probability of a type 2 error is the probability that we get a value for our distribution less than that critical value of 104.93, given that the mean is 106. Remember, we were just presupposing this mean of 106, but that value is taken from sort of the literature on what these companies thought the mean would increase by. And so you standardize it, and you get a z-score of negative 0.0355, which approximately is 0.361. So this area here is the probability of making a type 2 error is 36%. So even if the training genuinely adds 6 IQ points, this study that we did with 25 participants misses it 36% of the time. Okay. Type 1 and type 2 errors go hand in hand. You cannot shrink both. Okay? So, here is, remember that critical value is here. And to the right, we have 5%. So this is our alpha level. And to the left, we had that 36%. And so we end up with a seesaw situation. If you demand stronger evidence, you can decrease the risk of making a type 1 error, but you increase the risk of making a type 2 error. Or you can go the other way. You can decrease the risk of making a type 2 error, but then you increase the risk of making a type 1 error. And so it's sort of like a seesaw. So with n fixed, n is our sample size, we have 25 participants, alpha and beta sit on a seesaw. Pushing one down lifts the other up. And so it's our choice, as lawyers, if you're thinking about the trial case, and as statisticians, to decide what level of risk and what kind of risk is acceptable to us. In the courtroom, making a type 2 error is considered less risky than making a type 1 error. But if you're a shepherd, crying wolf when there's no wolf there is less of a problem than not crying wolf when there is a wolf there. So a type 2 error, if you're a shepherd, is much worse than a type 1 error. And so we need to decide on these things before we run our statistical analyses. And here it is all in plain English, hopefully. Just to really, with the lumosity training. So down the left, the study says it works. That means we're rejecting the null hypothesis. The truth is that the training is useless, then we've made a type 1 error. Similarly, we can make a type 2 error, would be the situation where we say, nah, we're not convinced that this does anything, but the app really did work. The training did work. And so in that situation, a program that truly was helpful gets shelved and doesn't get used. So which error is worse? Well, as we spoke about, in this example, a type 1 error was worse because Lumosity probably put a lot of money into funding these things, and it was an expensive error to make. The only thing that we can adjust is alpha. So we need to weigh the real world cost of each error when we do these statistical analyses. Okay, so how do we fix these problems? Well, as we can see, it's sort of a balance. We're balancing our type 1 and type 2 error rates. When why n breaks the seesaw. So if we take larger samples, we can make both the bell curves narrower. And this comes back to the central limit theorem, which I'll put a link below. The curves overlap less, so alpha holds at 0.05 and beta region shrinks 2. So if we did the same test, but we had 100 people, crunching the numbers for our type 2 error, we get 0.09009. So quadrupling n cut the miss rate from 36%. Remember, the miss rate is this idea of a type 2 error, from 36% down to 1% with alpha unchanged. So with the brain training, the studies were small, so they were prone to type 1 error flukes. And too weak, we say weak, they didn't have the statistical power to measure effects precisely. And so when Owen comes along and uses 11,430, the effects vanished. The moral of the story, sample size is the honest scientist's best defense against both kinds of errors. And you will see why here that's the case, because we're going to draw a picture. Because if you have narrower curves, there's less overlap. So this was the original situation with n equals 25. If we quadruple it, we end up with this situation. So quadrupling the sample, the standard deviation halves from 3 to 1.5, so we get narrower curves. And the curves barely overlap. So we're holding alpha at 0.05, the gold region, the gold miss region all but vanishes, and beta falls from 0.361 to 0.009. So our chance of making a type 2 error is significantly decreased when we take larger samples. Remember, alpha stays unchanged because we have to decide, generally 0.05 is considered our acceptable limit for our p-value. And that's really it. Hopefully that made a bit of sense. Here's the summary. Alpha is the risk of crying wolf. Beta is the risk of missing the wolf. Only a bigger sample tames both. Quite poetic. Yeah, and so hopefully that made a bit of sense. If you found that interesting, and hopefully it made a bit clearer some of these concepts, which can be quite challenging, give us a thumbs up, reach out if you've got any questions, and I'll talk to you soon.